When you think about concrete, what comes to mind? Sidewalks, bridges, maybe just a boring gray block. But what if I told you that this ancient material is actually at the heart of a massive high-tech revolution? We're going to dive into how scientists are completely reinventing concrete, making it stronger, tougher, and yeah, even smarter. So, is it really just a simple mix of sand, gravel, and cement? I mean, for centuries, that was pretty much the whole story. But today, with skyscrapers that touch the clouds and bridges that need to last for generations, simple just doesn't cut it anymore. The material that literally built our modern world is getting a very serious upgrade. You see, the real challenge is that we need materials that don't just stand up, but can handle decades of stress, extreme weather, and all kinds of unexpected events. And that's why scientists are going back to the fundamentals, basically re-engineering concrete from the inside out to push its performance to a whole new level. Okay, so let's start with strength. Now, concrete is fantastic when you squeeze it, that's called compression, but it's actually pretty weak when you try to pull it apart. That's why we add steel reinforcement bars, or what everyone calls rebar. And the real secret to its strength is all about the bond, that partnership, between the steel and the concrete surrounding it. It's amazing how a simple design change can make such a huge difference. See, early rebar was smooth, but research quickly showed that deformed rebar, the kind with all those ridges, creates a way, way better bond. You can think of it like the tread on a tire gripping the road. Those ridges create a physical, mechanical lock with the concrete, and that dramatically improves the whole structure's strength. So, that partnership between rebar and concrete is absolutely key. But of course, researchers are always asking, can we do even better? What happens if we start mixing and matching different materials to create something that's greater than the sum of its parts? Well, the answer is pretty fascinating. A recent study looked at these hybrid systems, combining traditional steel with an advanced material called glass fiber reinforced polymer, or GFRP. And the result? It wasn't just an average of the two. No, the hybrid system was significantly stiffer and stronger than either material could be on its own. It's like creating a kind of super reinforced concrete. But look, pure strength isn't everything. We also need toughness, which is all about a material's ability to resist fracturing. In concrete, that really means stopping those tiny, almost invisible cracks from growing into catastrophic failures. And the secret weapon for that? Tiny little fibers. Researchers have a great name for this, fiber bridging. Here's how it works. When a microcrack starts to form, the thousands of tiny fibers scattered throughout the concrete act like microscopic stitches. They physically bridge the gap, holding the material together. And this is essential for creating a concrete that bends a little before it breaks, making it more ductile and a lot less brittle. And the science is always evolving to find the absolute best type of fiber for the job. While there are a lot of options out there, recent research shows that when it comes to holding strong after a crack is already formed, a really critical measure of toughness, steel fibers currently have the edge over their polymer counterparts. It's all about finding the right stitch for the right wound. Okay, so we've made concrete stronger and tougher, but what about making it last longer? The biggest challenge here isn't some single big event, but a slow, relentless attack from the environment itself. One of concrete's greatest enemies is corrosion. It all starts when contaminants, like road salt on a winter bridge, seep through the concrete and finally reach the steel rebar inside. The steel then starts to rust, and here's the real problem. Rust actually takes up more space than the original steel. This expansion creates this immense internal pressure, cracking the concrete from the inside out. It's truly like a cancer for the structure. But it's not just about chemistry. Something as simple as water and temperature changes can be just as destructive. In colder climates, water gets into the tiny pores of the concrete, it freezes, it expands, and then it thaws. This happens over and over and over again, winter after winter, just slowly breaking the material apart from within. So how serious is this? Well, upcoming research puts a number on it, finding that these repeated freeze-thaw cycles can reduce that crucial bond strength between the rebar and the concrete by as much as 40%. Understanding that kind of degradation is absolutely critical for designing safe infrastructure in any region that has to deal with freezing temperatures. All right, this brings us to our final and maybe the most futuristic upgrade. We've made concrete stronger, tougher, and more durable. Now we're making it smarter. And how are we doing that? By using artificial intelligence to predict its performance before a single drop is ever poured. For decades, the only way to know how a new concrete mix would perform was to, well, make it, wait for it to cure, and then physically crush it in a lab. It was slow, it was expensive, and it was pretty wasteful. Today, we're seeing this massive shift away from the physical lab bench and into the digital world of the laptop. And this is where it gets really powerful. As this quote shows, researchers are training sophisticated AI models, feeding them huge datasets of past experiments. These neural networks can now predict properties like compressive strength with incredible accuracy, just by looking at the recipe of the mix. The practical benefits here are just enormous. AI can help us optimize brand new concrete mixes for very specific jobs. It can predict how they'll hold up over decades of use, and it can drastically cut down on the time and money we spend on physical testing. This whole digital revolution is making innovation faster, cheaper, and ultimately a lot more effective. So, from a simple rock to a high-performance material that's predicted by AI, concrete has come a seriously long way. It really makes you wonder, if our materials can get this smart, how long is it until our buildings start using that intelligence to help design, monitor, and maybe even repair themselves? Now that's something to think about.